All right, if those of you are watching this, try and record this lecture. We are talking about recurrence relations, something called recurrence relations or difference equations in mathematics. And first, let's point out what we're talking about. Here are some notations that I need to point this way now. There are some notations that we use when we're talking about sequences, and sequences are functions whose domain is an integer. So not like f of x equals x squared that's defined on all real numbers. A sequence is only defined, say, on the non-negative integers or the positive integers. And so we could use our regular function notation a of n, but more typically we write a sub n, and that's already come up a number of times in this class. This is called an explicit definition of a sequence. So let's see, explicit and implicit. Explicit shows everything, right? Implicit, something is implied or hidden. So here, explicit, if I want to know what a sub 1000 is, the 1000th term in this sequence, I just go to the right-hand side, plug in n equals 1000, immediately crank out the number, and we're done. But an implicit form or a recurrence relation looks like this. It gives the term in the sequence in terms of the previous term. And so you need something to get started. So this sequence might start at 2, and then this tells you how to get a sub 1 in terms of a sub 0, and a sub 2 in terms of a sub 1, and a sub 3 in terms of a sub 2, and you keep going and going and going. But it's awkward. Now if I want to know a sub 1000, I have to take a sub 0 and compute a sub 1. Take a sub 1 and compute a sub 2. Take a sub 2 and compute a sub 3. A sub 3 gives a sub 4, and so on, all the way up to a sub 1000. So usually an implicit form is not as desirable as an explicit form. We'd like things to be given explicitly when possible. But quite often when you're first writing something down, like if you're counting something, sometimes an implicit form is the most natural thing to do. So you do that the easy way first, and then you work on it and try to get it explicitly. First thing I want to talk about is how to check when we actually have the right explicit form. So here's an implicit form. Here's an implicit form. I keep pointing to the screen, forgetting that I need to use my pointer. And I want to show that this actually is an explicit form, or in other words, this is a solution to the problem being stated here. So how do you show something's a solution? If I just wrote down a polynomial x squared plus equation plus 2x plus 7 equals 9, and I claim that x equals negative 2 or whatever is a solution, may or may not be, probably isn't, but how would you check? Plug in, all right? So you take everywhere you see an x in this equation, you plug in negative 2, and you check if the equality is actually true or not. This one looks like false, right? Yeah. So let's do the same thing. Let's take this expression for a sub n and plug it in everywhere we see an a sub n. We should probably first check a sub 0. So our claim is that this would be 9/4 times 5 to the 0 minus 1/4. So what is that? This is 9/4 minus 1/4 is 8/4 is 2, and that checks. That's what we are claiming that it is. And now we'll check for other values of n. The left-hand side is a sub n, but I'm claiming that that's 9/4 times 5 to the n minus 1/4. And the right-hand side, and we're trying to see if we get the same thing on both sides, the right-hand side is 5 times, so careful here, this expression tells me what a sub n is. So when I want a sub n minus 1, it means I have to replace the subscript n by n minus 1, and so that comes here in the exponent. So this is 9/4 times 5 to the n minus 1 minus 1/4. And then plus the 1 coming from the recurrence relationship. So 5 times a sub n minus 1 and then plus 1. Are we good so far? So I'm trying to show the recurrence is true here. And so I'll keep working on the right-hand side a little bit and see if I can make it look like the left-hand side. So first, let's distribute the 5 through the expression in brackets. And what happens here? I have a 5 times this first term. It's a 5 to the 1 times a 5 to the n minus 1, so the exponents add, right? And we get 9/4 times 5 to the n minus 1, but then plus 1. And then minus 5/4, and then plus 1. But of course, this 1 is 4/4, and so minus 5/4 plus 1 is minus 1/4, and there we are. Tessa.
You used the example of like at the top of like plugging in X, like for this one.
Mm-hmm.
So you said you were just plugging that in, like how?
Good question. This algebraic equation, if I'm asked to solve it, the answer is a number. And so I take my proposed number and plug it back in and see if I get the same number on both sides. This recurrence relation, the solution is a function. And so I take the function and plug it back into both sides and see if I get the same expression on both sides. Same concept, but kind of one level of complexity up. So, later, we're going to spend several days on this. Later, we'll talk about how to solve these. In other words, if I had this recurrence, how did I get this solution to begin with? But for now, it's comforting to know that if we do have an answer or think we have an answer, we can easily check it. Just plug it back in and see if the equation is true. Let's spend the rest of the time today showing where these things come from. By the way, this expression is called the recurrence relation. To recur, like the a sub n reoccurs, it comes back again on the right-hand side. And this starting value or initial value is what you get, what it takes to get you going. So this question asks to find a recurrence relation and one or more initial conditions to describe the following. I'll just read it. An annuity, which is just an investment, mostly for retirement, with a starting value of $10,000 earns 9% annual interest. We're going to work in months in this problem, so the first thing I should do is divide by 12 to convert from years to months. Compounded monthly, and on the last day of each month, we take $250 out of this. Let B sub n be the amount in the account at the end of the nth month. And I want to write a relationship that shows what's happening month by month by month. So the answer will be an expression in terms of n. So let's write the initial condition first. Actually, that's the easiest usually. B sub 0, what do I have to start out with? $10,000. And now B sub n. So now I'm trying to relate this back to, this is how much I have at the end of, say, this month. I'm trying to relate it back to how much I had at the end of the last month. So what happens here? Well, first of all, I have what I had last month, but then two things happen. One is that I earn interest. So that's coming to me, so it's a plus. And how much interest? Well, 9/12 this is like 0.75%. So as a decimal, which is how I should work with it, 0.0075, that's the monthly interest rate. And if I multiply that by the previous balance, B sub n minus 1, that tells me how much interest I earned. So this is from last month. This is interest earned. And then finally, the whole point of this investment is to generate some income for me so that I have something to live on in retirement. So I'm spending this down, so minus, and $250 is coming out each month. So these two things together would allow me to calculate way into the future, 1 month at a time, and find out how much I'll have 100 months from now or 500 months from now. And an investment advisor, of course, would use, okay, is this enough? Are you going to run out of money, or are you going to build up money, or stay even, or whatever? Does that make sense? All right, so we can come back later to talk. Let me simplify it just slightly. The first two terms are like terms, so I could write this as 1.0075 B sub n minus 1 minus 250. And we can come back later and talk about how these things can be solved. You okay? Okay, it'll take a little doing. You could use a computer program, a spreadsheet like Excel, as a good way to just calculate numbers, but we'll actually solve these and get an expression in terms of n. Next example, Fibonacci's rabbits. So you need just a little bit of history. Fibonacci, an Italian in the 1200s, as it says, takes a trip somewhere in the Arabic world. I forget just where, to Iraq, I believe, to Baghdad, I think. Anyway, comes back to Europe and notes that Arabic mathematicians or mathematics at the time is far more advanced than European mathematics. European mathematics is sort of in the Middle Ages and so on. And so writes a book which is tremendously influential, brings a lot of ideas, and in some sense maybe helps start the Renaissance a little bit, all these fresh ideas coming in. Also, particularly important because up until this time, Europe was still using Roman numerals. If you've ever thought about trying to do long division in Roman numerals, it's just a nightmare. And so he brings back the Hindu-Arabic number system, which we use, and commerce starts to boom just because people can actually reasonably calculate things. Tremendously important book. Anyway, as an aside, one of the examples that he has in the book is these rabbits. So you have an initial pair, male and female rabbits, and we'll make some big assumptions here to simplify the problem. We assume that all rabbits need 1 month to reach reproductive age, and then after that, each month they will have one pair, or 2 babies, one each male and female. And you also have to assume that these rabbits have no scruples about incest. So they marry their brothers and sisters and so on. And the question is, how many pairs of rabbits do I have at the end of the nth month if I start with one pair? So here's a picture that shows after the second month, you still have one pair. They've just grown up. And now then, here's the original pair plus first set of babies. And you see numbers going 1, 1, 2, 3, 5. And the next one would be, have you seen this before, the Fibonacci sequence? Okay. And then, okay. So let's see if we can actually write an expression for that. So f sub n, the number of pairs of rabbits at the end of the nth month. Well, these rabbits never die. Immortal rabbits, it's a scary thought. And so one thing you have at the end of the nth month are all of the pairs that were alive in the previous month. So f sub n minus 1. These were rabbit pairs from last month. But then plus you also have babies. And the question is, how many pairs of babies do we have? So remember that each mature pair of rabbits is having exactly one pair of babies every month. So how many baby pairs do I have? It's the same question as how many mature rabbits did I have in the previous month? Well, what's a mature rabbit? It's a rabbit that's at least 1 month old. And so it's the same question as how many pairs did I have 2 months ago? I'm going to put an f n minus 2. These are number of pairs of adult rabbits last month, because those are the ones that have one pair of babies each. And you can kind of see it in the picture, like why, for example, is this newborn happening? Because 2 months ago there was a pair of rabbits who have 1 month to grow up and then 1 month to have babies. And why is this pair here? Because 2 months ago there was an adult pair. Okay, so survivors plus babies, and babies are the same as the number of mature rabbits in this case. Okay, so notice this recurrence actually goes 2 time steps in the past. To show how many rabbits I have in month 6, for example, I need to know how many rabbit pairs I had in month 5 and back in month 4. So to give initial conditions, I had better give 2 of them. How many do we start with? 1. And how many do we have after the first month? Still 1. And then all of this together lets me crank out the rest. So what's f sub 3? What's f sub 3? It's f 2 rather. It's f sub 0 plus f sub 1. It's 1 plus 1 is 2. And that's the familiar pattern if you've seen the Fibonacci numbers, that each number is the sum of the previous 2. Okay? Hugh. You sure? Okay. Third example, let's talk about bit strings. So this is computer term, bit, binary digit It's just a 0 or a 1. So when I say bit strings, I mean something like this sequence of zeros and ones. And what I want to do is write an expression for the number of bit strings of length n that have no two consecutive zeros. So this is not a bit string like the ones I'm trying to talk about, but 1 1 0 1 0 1 1 is an example of a bit string of length 7 that has no two consecutive zeros. So let's try to write down the idea maybe in English first and then translate it into symbols. And I'm trying to write this recursively, which means to go back a step. So for problems like this, I'd be thinking about, well, how many bit strings do I already have? And then I tack on one more bit to see how many bit strings of the next larger length do I have. So if I want to talk about n bit strings, I need to go back and talk about shorter strings, like n minus 1 bit strings. So let's break this apart into what I can end with, because you see, I have to avoid consecutive zeros, and so it makes a difference whether I'm going to try and put a 0 on the end or a 1 on the end. Right? If I want to put a 1 on the end, I just do it. But if I want to put a 0 on the end, I have to worry about whether the previous bit was a 0. If it was, then I can't put another 0 onto the end of that. That'd be double 0, which has to be avoided. So let's say that a sub n is number of strings ending in a 1 plus number of strings ending in 0. Now, in terms of, and here I'm talking about strings of length n. So in terms of strings of length n, how many are there that end in a 1? How could I get such a string? It would be to just take a string of length n minus 1 and just slap a 1 on it. So this is a sub n minus 1, you see? Taking all strings of one fewer bit and just slapping a 1 on the end of it. So I start with what's in red and I slap a 1. If here is what I had in red, I can slap a 1 on it, and that's legal. Plus, okay, now I want to slap a 0 on the end. So let's think about that for a moment. What has to be true if I'm going to do something, something, something 0? Then that has to be a 1. And are there any restrictions on what's here before that 1? No, because I know the thing in brackets here to the left already was a legal string. It had no consecutive zeros. So I can do, if I'm going to construct an n-bit string ending in 0, I can do anything legal that I want. Then the next to the last bit has to be a 1, and then the very last bit will be the 0 that I'm trying to put on there. So how many of these are there? I can do anything I want for the first n minus 2 bits. So plus a sub n minus 2. So I take an n minus 2 bit string and then I slap on a 1, 0, and that gives me a legal string ending in 0. Okay, that's a little tricky. Again, this bumps me 2 time steps into the past, or 2 lengths shorter. So I had better come up with 2 initial conditions. How many legal strings are there of length 1? And legal means no 2 consecutive zeros. Well, of length 1, there's a 0 or a 1. So there are 2 choices. For strings of length 2, 0, 0, but not legal, right? And then 0, 1, 1, 0, or 1, 1. There are 3 of those. So it's almost like the Fibonacci numbers. Each term in the sequence is the sum of the previous 2, but it starts out differently. Make sense? All right. Thanks for coming. We'll stop there.